Welcome to Physics and Reality with Prof. Stuckey. I'm Emeritus Professor of Physics, Dr. Mark Stuckey, and in this video I'm going to explain how the weird phenomena of length contraction, time dilation, the relativity of simultaneity, quantum superposition, entanglement, and complementarity all result from no preferred reference frame, aka the equality of all perspectives, aka the relativity principle. To keep this video short, I will omit many details. You can find those missing details in our book, Einstein's Entanglement, published with Oxford University Press in 2024, as well as papers linked in the video description, or you can watch my 5-episode YouTube video series on the book. In episode 3 of that video series, I explained how Einstein solved the mystery of length contraction in principal fashion, giving us special relativity in 1905, as introduced in these textbooks and John Norton's course on special relativity. Accordingly, the mysteries of length contraction, time dilation, and the relativity of simultaneity all follow from the relativity principle, aka no preferred reference frame, or NPRF for short. To solve the mystery of length contraction, Einstein gave up constructive efforts in despair and turned to a universal formal principle. Here is how Valli-Allori describes a constructive theory per Einstein. In the late 1800s, most physicists believed the experimentally discovered fact that everyone measures the same value for the speed of light c, regardless of their motions relative to the source, was due to the shortening of objects as they moved through the luminiferous ether length contraction. This explanation via a causal mechanism is what Einstein meant by constructive efforts. Einstein gave up such constructive efforts in despair and instead sought a universal formal principle to explain length contraction. Here is how Allori describes a principal theory per Einstein. Thus, today, the principal theory of special relativity provides a principal explanation for length contraction. In other words, you have a compelling fundamental principle, the relativity principle, justifying an experimentally discovered fact, the observer independence of c, the light postulate, which dictates your kinematics, which is the Lorentz transformations, solving the mystery of length contraction. Lorentz complained that Einstein simply postulates what we have tried to explain via constructive efforts. That is, that everyone measures the same value for the speed of light c regardless of their relative motions. Recall that light postulate is what they wanted to explain using length contraction caused by the luminiferous ether. But notice Lorentz acknowledges that Einstein, quote, may certainly take credit for making us see the manifestation of a general and fundamental principle, i.e. the relativity principle. So Lorentz was willing to accept Einstein's light postulate because it was so strongly justified by a compelling fundamental principle, the equivalence of all perspectives. Given the enormous success of special relativity, Carlo Rovelli suggested we try a similar approach to quantum mechanics. He says here, quantum mechanics will cease to look puzzling only when we will be able to derive the formalism of the theory from a set of simple physical assertions, postulates, principles, about the world. Therefore, we should not try to append a reasonable interpretation to the quantum mechanics formalism, but rather to derive the formalism from a set of experimentally motivated postulates. And you can see he was inspired by what Einstein did with the Lorentz transformations for special relativity. Specifically, Rovelli suggested we use information theoretic principles, and the first such axiomatic reconstruction of quantum mechanics via information theoretic principles was produced in 2001 by Lucian Hardy. And many have been produced since, with the first fully rigorous complete reconstructions, according to Marcus Mueller, published in 2011. They can all show how the Hilbert space formalism of quantum mechanics follows from some experimentally motivated postulate, but I will focus on those that start with the quantum binary digit of information, or qubit, according to Olivier Derigal's discreteness and correspondence requirements applied to a property of electrons called spin, as introduced in episode 2 of Einstein's Entanglement. Here is Derigal's experimentally motivated discreteness requirement for a spin 1/2 qubit. As electrons pass through Stern-Gerlach magnets, they are deflected up or down, never anywhere in between. This is Derigal's discreteness requirement. If we create a spin 1/2 qubit in the state psi equals z plus using Stern-Gerlach magnets oriented along the positive z axis, our spin angular momentum is +1 z hat, in units of h bar over 2 equaling 1. Now proceed to make a spin measurement with the SG magnets oriented at b hat, making an angle beta with respect to z hat, as Dergel describes. The outcomes of the spin measurement will still be up or down along b hat, no matter how the SG magnets are oriented in space. This is Dergel's discreteness requirement. According to classical mechanics, we expect to measure the projection of +1 along b hat, or +1 cosine theta. But we can't measure anything other than plus or minus 1 due to Dergel's discreteness requirement, contra the prediction by classical physics. Instead, we recover +1 cosine theta on average, quote, in order that the average angular momentum in the direction beta be equal to the projection of the initial angular momentum on this direction. This is Dergel's correspondence requirement. Thus, discreteness and correspondence give us qubit superposition at the basis of the Hilbert space formalism for quantum mechanics. But why discreteness? Here's what Dergel says. From a physical point of view, discreteness is a non-trivial assumption. In the present state of this approach, we should probably content ourselves with the insight that quantum discontinuity, if it is admitted as a fundamental feature of the microworld, and if it is complemented with natural axioms concerning the relation between micro and macroworld, in other words, the correspondence requirement, necessarily leads to quantum mechanics as we know it. Would Lorentz have accepted this? In other words, we don't have any justification for discreteness, but that and correspondence give us qubit superposition and QM as we know it, so maybe we just have to let the end justify the means? But to stop the derivation at this point is analogous to deriving the Lorentz transformations from the observer independence of C without justifying that experimentally motivated postulate with the relativity principle in Maxwell's equations. And you saw from Lorentz's quote earlier that no one would have taken Einstein's derivation seriously in that case. So we need a justification for discreteness as compelling as the relativity principle. And we have just that. As Steven Weinberg points out, measuring an electron's spin via Stern-Gerlach magnets constitutes the measurement of, quote, a universal constant of nature, Planck's constant h. Thus, Dergel's discreteness requirement entails the observer independence of Planck's constant h between inertial reference frames related by spatial rotations, i.e., between different spatial perspectives. And thus, we justify discreteness with NPRF and Planck's radiation law. So, Knight could mirror his introduction to special relativity for an introduction to quantum mechanics. Consequently, the weird phenomena of time dilation, length contraction, the relativity of simultaneity, quantum superposition, entanglement, and complementarity are evidence that reality does not lead to a fragmented collage of our different subjective experiences from our different perspectives. Rather, reality leads to the comprehensive and coherent integration of our different subjective experiences according to the equality of all perspectives. No one has exclusive access to the correct laws of nature, finding the uniquely correct values for the fundamental constants. And that means what we must discover about reality will, in some cases, be very weird.